Good morning, good afternoon, or good evening, everyone. Welcome once again to the RTDS Technologies User Spotlight Series. This is week number 8, and I'm happy to welcome you all for 2 exciting user presentations about application of the RTDS simulator. My name is Katie Sidwell, and I am a simulation specialist on the sales and marketing team at RTDS Technologies. If this is your first time joining us for this webinar series, I'd like to direct your attention to the Q&A widget. It should be in the top left-hand corner of the webinar interface, or you can access it from the icon toolbar at the bottom of your screen. And this Q&A widget is the spot where you should be putting your questions for our presenters. They will be answering questions all throughout the presentations today, and then at the end of both presentations, we will do a live Q&A and discussion to discuss some of the questions that you've submitted. If you are joining us on demand, if you are listening to this webinar after the fact, you can also submit questions via the Q&A window, and we will get back to you via email. So please do submit lots of questions and use that Q&A widget. The chat widget is not where you should be putting your questions, but we would like to say hello to everyone in the chat window and get to know you, so please feel free to introduce yourself. Let us know where you're joining from today. I know we always have quite a global audience, so it's great to hear where everyone's coming from. If you'd like to access the slides for today's presentations, you can do that using the Handouts widget. In the icon toolbar at the bottom of your screen, it looks like a couple of pages, and clicking it will allow you to access the PDF files of the slides. We have 2 smart grid related presentations today. The first one is IEC 61850 related, and the second one deals with wide area measurement systems. So without further ado, I'm pleased to introduce our first presenter. From the comfort of your own homes, please give a warm welcome to Dmitrii Blagorazumov of Moscow Power Engineering Institute. In 2016, Dmitrii graduated from Chuvash State University on the Relay Protection and Automation of Power System Department, where he received his bachelor's degree. After that, he went to the Moscow Power Engineering Institute, or MPEI, where he received a master's degree in 2018. During his studies at the university, he began working as a trainee of maintenance and test engineering. After graduation, Dmitrii got a position of application engineer at MPEI. He has 4 years of experience in power engineering. During this time, he's developed a number of skills, including development of relay protection logic diagrams to implement protection automation and control logic, competence with utilization and configuration of relay protection devices from different vendors, and RTDS model development. In addition to engineering tasks, he teaches practical and laboratory classes at the university in relay protection and the theory of automatic control. Please welcome Dmitrii Blagorazumov with his presentation, Development of a New Method for Transmission of Current and Voltage Measurements in accordance with IEC 61850, providing reduction of traffic to the process bus.
Thank you very much for your introduction, Katie. My name is Dmitrii Blagorazumov. I am engineer from Moscow Power Engineering Institute, Department of Relay Protection and Automation of Power Systems. Let's get started. If you have any questions, please feel free to ask me at the end of the presentation. I will be glad to discuss it and see if there are any fresh ideas on it. The theme of my presentation is development of the new method for transmission of current voltage measurements in accordance with IEC 61850, providing reduction of the traffic to the process bus. Describing this process, it's necessary to start with the idea of development and implementation of digital substations based on the application of the IEC 61850 standard is widely used all over the world. The modern approach to digital substations involves the use of a sufficiently large number of merged units and intelligent electronic devices. The data transfer between them is carried out through the LAN using the SV and GOOSE protocols. While developing the LAN structure, it's needed to take into account the amount of traffic produced by SV streams. There is a problem of high traffic with SV. A large number of expensive switches are required, and it's difficult to create an optimal LAN. To solve these problems, it's necessary to develop a new method of transmission for measurements. Moving on to our next slide, transmission of measurements via SV protocol requires a high data transmission frequency, which leads to high traffic. The scientific novelty of the work is to change the principle of calculating phasor values. The RMSU node has been transferred to metric unit, which has become more intelligent. We will talk about it a little bit later. Now we will look at the structural scheme of the PEC complex when transmitting measurements via SV protocol. For redundancy of measurements, two metric units are used, which are connected to different secondary winding of current transformer. To resolve the discrete information, we may also use two metric units. And independent QN with support for protocol GOOSE should be used for transmission of discrete information, in particular commands turn off the switch, the position of the switch, and operational logs. In order to understand this process, this slide shows the structure scheme of the PEC complex when transmitting measurements via GOOSE protocol. Through the use of a new method of transmitting measurements, each metric unit perform the function of input and output of discrete and analog signals and control switching devices. To transmit measurements and discrete signals, a single LAN is used. Due to the presence of separate LAN in one option for the transmission of discrete messages, there is an additional component that affects the reliability of the system as a whole. For testing a new method of transmitting current and voltage measurements, the RTDS was used. The slide shows the scheme of connection RTDS complex to develop a prototype of PEC. Metric unit which implements a new method of transmission of current and voltage measurements is modeled in RTDS. Receive and process of measurements of current and voltage transmitted using GOOSE messages implement in PEC prototype. Information about switch position as well as commands for switching of all the transmitted as GOOSE messages via the process bus. Moving on now, three different devices were used for testing. Device Protection Series BE ECRA, the leading Russian manufacturer, and two industrial computers with developed software that implements the function of relay protection devices and data transfer protocols. This slide presents a logical device for overcurrent protection and distance protection realized in ID prototype. It has to be said that the distance protection logic device consists of the following logical nodes. The RMSU logic node is designed for calculation RMS values based on the application of the Fourier filter. Logical node SVTR is designed to check the integrity of voltage circuit. Logical node car PSB and DSH PSB provides information of resolution or blocking signals to account for the mode of swinging. Logical node ZDIR is designed to perform the function of power direction relay. Logical node PDIS is designed to perform distance protection function to stage. The overcurrent protection logic device consists on the following logical nodes: RMXU, logical node RD redesigned to perform the function of power direction relay, and the logical node PTOC is designed to perform the function of overcurrent protection relay with control of direction and application of voltage start, also two-stage. Logical node PTRC is designed to merge the signals of operation and start of logical devices PTOC and PDIS. You may find the detailed description is presented logical nodes at IEC 6150 chapter 7.4. I strongly believe that to reduce the load of communication channels with switch streams during the transmission of current voltage measurements, a new method based on GOOSE message is needed. In logic unit, there is calculation of phasors values of current voltage for the cycle of industrial frequency, 20 milliseconds. Then calculate the phasors of current voltage with the use of GOOSE message are transferred to the PEC terminals with a certain periodicity. Transmission of GOOSE messages in normal mode is carried out at intervals of every 1 second, parameter T0. In the event of a technological failure, for example, a short circuit, fault detector is triggered, which determines the fact of an emergency situation. When a fault detector is triggered, the logic unit calculated current voltage phasors using a buffer instantaneous values. Generation of the GOOSE message occurs as long as a fault detector in logic unit registers the presence of an emergency situation. Now we will look at the GOOSE message structure using the new method of transmitting measurements. This face the fact that phasor measurements can be represented as amplitude and angle, or real and imaginary parts. In this case, 12 orthogonal companions are presented, 2 for each phase. I would like to show you the point that each logic unit has a fault detector that is triggered upon the accuracy of process disturbances. To implement the proposed method as a software, a wavelet transformer is used, since it allows to analyze the transient process and determine with a given accuracy the moment of fault. The application of fault detector for various types of disturbances, short circuit, load power, non-sinusoidal modes, was considered. To simulate the above-mentioned disturbances, the real-time digital simulator was used. It was found that the moment of accuracy of an emergency is accompanied by the maximum of the function obtained by a Morley wavelet transform. Depending on the type and the location of the short circuit, different times of the wavelet function maximum was obtained. The short circuit time selection algorithm determines the minimum time to reach the maximum of the wavelet transform function for each phase of current and voltage. Let me do a remark that the other modes were also considered, line disconnection case and real short circuit case. I would like to show you a test installation with two prototype ID, old and new method transmitting measurements, and echo terminals. There are also switches for implementing the process bus. Yes. It has been said that is at the beginning, estimation of the execution time of the PEC function and transmission of control commands was made on the example of a simple short circuit. The variance measurements transmission presented in this table were investigated. This figure shows the diagram of the accurate terminal operation and two PAX device prototype. We should realize that the result of the comparison of the PAC action time and the transmission of the trip commands show that the new method for measurement transmission ensures the required speed of the distance protection. Compared to SV data transmission, a new method of current and voltage measurements, transmission for PAC allows to reduce the peak load of the network in emergency conditions by more than 300 times for one bay. For the substation as a whole, the process bus load can be reduced by 1,000 to 3,000 times, depending on the substation scheme and the number of bays. Compared to three streams, in normal condition, reduce the load of the process bus and be more than 2,000 times, depending on the scheme of the substation and number of bays, while maintaining the required spec algorithm speed. Testing of PAC devices was conducted on the example of 110 kilovolt substation. Here we can see the developed schemes in drafts and runtime. I have to say that the following cases were considered: face-to-face fault AB at K2, increasing power for line 2, and external fault at K1. Relay protection connection in this point. As we can see in the first case, in the face-to-face short circuit AB at K2 was considered. Let me navigate you to the diagram number 1. Current of the line to be protected, logical short circuit signal, and triggered signal from three terminals: prototype SV, prototype GOOSE, and ECHRA. To sum up, then, the result of the comparison of the PAC action time and the transmission of the trip commands shows that the new method for measurement transmission ensures the required speed of the distance protection about 15 and 20 milliseconds, depending on moment of short circuit. We should understand that when the fault detector in emerging unit is activated, the current and voltage phasors are calculated for the cycle of industrial frequency using the buffer of current and voltage sampled values. Next, the newly calculated phasors values are periodically sent as GOOSE message every 10 milliseconds. The generation GOOSE message occurs as long as the fault detected in emerging unit senses the presence fault. In case of increasing power or external short circuit response of the PAC devices is not observed. This is correct operation of the PAC devices. On one diagram the following is presented: current of the line to be protected, logical short circuit signal, and triggering signal from three terminals: prototype SV, GOOSE, and ECHRA. Sending of GOOSE message is normal mode operation is done every 1 second. In this case, the current and voltage phasors are not required for the operation packed devices. I would like to end by emphasizing the main points. The new method for current and voltage measurements transmission, meeting the requirements of IEC 6150 standard and providing a reduction of the information load on the LAN in comparison with IEC 6150 standard 9.2 LE was proposed. I think we have seen that we should consider that the new method for measurements transmission using GOOSE messages ensures the required speed of the distance protection algorithms and reduce the workload of the process bus LAN in emergency condition by more than 1000 times, depending on the substation scheme. Application of the developed method of data transmission from measuring transformers allows to reduce the number of switches in the LAN, and also to use the combined architecture of the bus station and process bus for the creation packs for digital substation. Thank you for your attention. So now I would be glad to hear your comments.
Thank you so much, Dmitrii, for that presentation. Our second presenter for the day is Devesh Shukla from the Indian Institute of Technology, BHU. Devesh Shukla graduated in Electrical and Electronics Engineering in 2012 and got his post-graduation in 2015 with Power Systems as a specialization. Presently, he's pursuing a PhD in Electrical Engineering from IIT Varanasi. He has delivered many talks and events organized by the IEEE student branch at IIT Varanasi. He has been the chairperson of IEEE Power and Energy Society's student branch chapter at the university. His area of interests include real-time ATC assessment and enhancement, near real-time load forecasting, quasi-static simulation of power systems, integrated transmission and distribution modeling and simulation, analysis and monitoring of integrated transmission and distribution, blockchain-based energy trading with its probable impact on the aggregated load profile, and ADC evaluation and estimation. Please welcome Devesh Shukla with his presentation, Monitoring, Analysis, and Control of Power Grids Using Wide Area Measurement Systems.
Thank you very much for your introduction. A very good morning, good afternoon, and good evening to all. I, as introduced by Kate, am Devesh Shukla, would be presenting the session on monitoring, analysis, and control of power grids using WAMS. I am a research scholar at Indian Institute of Technology, Banaras Hindu University, working under the supervision of Professor S.P. Singh. I will start my presentation with a brief overview of the various aspects that we would be uncovering during the session. I will start with the situational awareness, where a brief discussion about the current power system scenarios would be discussed, followed by a brief introduction to the application which we have considered for monitoring, analysis, and control. That is, we have considered available transfer capability for this purpose. We have developed the pseudo PMU emulation for quasi-static simulation. We will discuss that, and then we will go into the details of real-time ATC estimation, where we will be discussing how the real-time ATC estimation have been implemented on real-time digital simulator. Power system monitoring is being regularly done to grasp the operational situation of the power grids. Availability of adequate information pertaining to the health of the system would ensure appropriate decision making by the power system operators. The complexity of the system monitoring has increased many folds, with major contributors being the emphasis on large-scale integration of renewable sources at both the transmission and distribution levels. integration of renewables increases the uncertainties of the system operation, at same time reduces the grid inertia. Large-scale integration of DG at distribution levels and appraisal of prosumer technology, the conventional distribution networks converts to active distribution systems. The active distribution networks with advanced monitoring and control capability, if allowed, could possibly inject power back to the grid at transmission levels. On account of such interaction, traditional methods of power system analysis monitoring developed with consideration of disjoint transmission and distribution would have to be revisited and recalibrated for adequacy. The increased renewable penetration also affects the power flow through the line, and hence the assessment of transmission capability remaining in the system becomes an important factor. The total available transfer capability can be defined as the power transfer capability remaining in the system over and above the existing transmission commitments. For example, we have considered here the total transfer capability, which comprises of transmission reliability margin, capacity benefit margin, existing transmission commitments, and available transmission capability. The available transfer capability can be estimated by subtracting the TRM, CBM, etc. from the total transfer capability. We have illustrated the significance of available transfer capability during real-time operation through certain examples. In our first example, we consider a 4-bus system with 4 loads PD1, PD2, PD3 and PD4 and generators G1 and G2. Now, here two lines, line 1 and line 2 have been shown. If there happens to be a fault on line 2, then the power flow through the line 2 would be obstructed and the power would be directed from G1 through the line 1. This would affect the available transmission capability of the system, and this will affect the transmission margin of the system. Similarly, a single generation plant would comprise of several generation units. If there is a contingency in one of the generation units, then the power flowing through the line 1 and line 2 would be modulated. As we can visualize that due to outage of one generator in the plant, the power flow through the line 2 has increased and power flowing through the line 1 has decreased. This will affect the transmission margin of the system. Similarly, when there is the presence of renewable generation, then also with changes in intermittent source of power generation, that is, if the wind velocity would increase, then it is expected that generation would increase. In such case, also the transmission capability remaining in the system would change. For example, if we consider this case where we have 4 loads and 2 generation plants, one is wind farm and another is conventional plant, and if the power increasing because of change in wind speed is allowed to flow through the line 1, then also the power flow through the line should be changing and the transmission capability margin would alter. Therefore, assessment of ATC is significant. Again, here we have illustrated the significance through the consideration of two different areas, area 1 and area 2, connected through two tie lines. Now here, if there is a fault on tie line 1, then the power would be forced to flow through the line 2, which would again affect the transmission capability of the system. Therefore, adequate information of transmission capability margin, that is available transmission capability margin, would empower the power system operator to take adequate decisions. Hence, the availability of real-time data for ATC is significant factor. If we want to evaluate the ATC from area 1 to area 2, then we would adopt the process illustrated in the schema shown here. Here we have shown area 1, 2 and 3. If we want to evaluate the ATC from source to sink, that is area 1 to area 2, then we would be increasing the load in sink area and corresponding generation would be increased in source area, maintaining the generation load balance mechanism. The same will be true if we reverse the scenario where area 2 becomes the source and area 1 becomes the sink. The available transfer capability is having two main aspects, that is economic and reliability aspects. If we focus on economic aspects, then reliability aspects is hampered, and if we focus on reliability aspects, then economic aspects is hampered. Further, there is one additional aspect to it, that is the resiliency. If we focus on economic aspect, then it also hampers the resiliency aspect of the grid. Therefore, adequate assessment of available transfer capability is significant. The ATC for power system operation can be controlled by changing the power flow through the lines. Therefore, it would be apt for the power system operator to have the optimal value of ATC in the network. Therefore, ATC estimation problem can be formulated as a optimization problem, a maximization problem, as illustrated in these equations. Here, N sink is the number of buses in the sink area, and Xi is the load at the ith bus. Xi0 is the initial load at the ith bus. The constants to which the power system, the optimization problem would be subjected are the equality and constants. These equality constants are the power flow constants. Similarly, inequality constants would be the upper and lower limits of the variables involved. Now, assessment of ATC requires data, offline data, to be generated. Now, offline data is required for training the ATC estimator. We have trained an ANN based ATC estimator for estimating the available transfer capability of the system, for generating the data of target ATC and emulated values of PMU information. We need a pseudo PMU emulator. Now, we have developed a model for pseudo PMU emulation for quasi-static analysis of our system. The PPMU emulator observes the various scenarios, or it would be apt to say the various snapshots in time, and acquires the information at the nodes at which the PMUs are placed. It archives the information and sends for further processing. The algorithm that has been used for emulating the pseudo PMU emulator is shown in figure 6. The solution or the snapshot information for various time instances are obtained using the power system network solver. The PMU emulator interacts with the power system network solver and acquires the information at the PMU nodes and archives them or sends them for further processing. Here we have shown two methods through which the PMU emulator could be implemented. One is the conventional method whereby we can use a for loop and archive the information if the node or the bus is PMU bus and fetch the data. This is a time consuming process. So we did not use this method, rather we propose a PMU emulation method whereby PMU emulator comprising of various PMU agents would acquire the information pertaining to the PMU nodes and branch or channels for which information has to be archived initially when the system is set. And when this information is archived and quasi-static simulation is done, then the PMU emulators directly go to the indexes of the nodes at which the PMUs are placed and acquire the information. Through this process, the timing is saved a lot. For example, we have shown here the sample cases of IEEE 30 bus, 24 bus and IEEE 118 bus system. The time employed for iterative algorithm is 0.0011 seconds, while that for PPM algorithm is 0.0007 seconds. We can see that the time involved is about half, and the time for iterative algorithm increases by large amount when the system size increases, but time required for PPM algorithm is much less than that of iterative algorithm. For real-time ATC estimation, as we have discussed earlier, we have used ATC estimator, which is based on artificial neural network. The artificial neural network that we have developed uses the radial basis function. A simple architecture of the ANN developed has been shown here. We have input features; those are fed to the feature extraction blocks. This feature extraction block provides the extracted features which is fed to the input layer, and from there it goes it is processed by the neural network and we get ATC as out. The feature extraction block is discussed here. In feature extraction is required to reduce the large number of feature sets to a small feature set. So when the power system network obtains the scenario sets during quasi-static simulation, it is the PPMU acquires the information of channel currents and nodes at which the PMUs are placed and sends it to the linear state estimator to formulate a complete set of feature sets comprising of the measured states and observed states. After this, these feature sets are fed to the SFA based feature extraction. This is sparse filter algorithm based feature extraction, which then goes to the NN estimator. The NN estimator estimates the ATC, and this is the overall process. Using this SFA algorithm, we have been able to reduce the number of features to the equivalently to the number of PMUs deployed in the system. For 24 bus, the number of features reduced to 7. 30 bus, it was reduced to 10, and for 118 bus, 118 bus, it was reduced to 33. Here, we have illustrated the software-based development of the proposed method using a schematic. As the quasi-static scenarios are subjected to the power system network solver, and power system network solver obtains the solution to different scenarios, the PPMU emulator acquires the information of the node at which the PMUs are placed, and concurrently the ATC optimization engine obtains the ATC value for that scenario and sends it to the ATC storage value, which prepares the target data, and the PPMU emulator sends the measured information to the linear state estimator, from where it goes to the VI block, which then sends it to the feature extraction block. After feature extraction block, the extracted features are sent to the neural network training block, from where, if the training of the neural network is complete, then it is exported as a trained neural network. And now this can be used for ATC estimation in real time. In case of practical implementation, the power system would replace the PSN solver, and the PPMU emulator would be replaced by the actual PMU. And then after data pre-processing stage, the ATC estimation would be done using the trained ANN. The developed method has been implemented on real-time digital simulation platform using GTNet PMU and GTNet SKT. Models have been modeled in RSCAD model, and we have used MATLAB control and command center. The MATLAB communicates with GTNet PMU through OpenECA platform. Now we will discuss the way through which we have interfaced the MATLAB to the GTNet PMU through OpenECA software. This is the PMU connection tester. For setting up the connection to PMU tester, we require host IP address, port, and device ID code. This information can be got from edit card parameter. Here we get IP address. This IP address is the host IP address, and from GTNet PMU configuration block, we would get the hardware ID and output TCP IP or UDP local port. The hardware ID would be the device ID code, and output TCP IP or UDP local port would be the port address. When we feed this value into PMU connection tester and we click connect, then we would start receiving the streams from the PMU, GTNet PMU. Once we receive or establish the connection, then we will save the file, PMU connection file. This file would be used by the OpenECA manager for communicating with the GTNet PMU. This is the OpenECA manager interface. We will use add device and load the connection file, PMU connection file, to add the PMUs to this OpenECA manager. We can use the graph measurements to visualize the incoming streams. For illustration of this, we have considered IEEE 14 bus test system. I have placed 3 PMUs, PMU1, PMU6 and PMU9 at buses 1, 6 and 9, and configured this OpenECA manager. The OpenECA manager would be interfaced with the MATLAB using the OpenECA data modeling manager. Using manage data structure, we would define 2 data structures, that is result data and source data. These data structures would be used for mapping the input data and output data. Once the input data and output data are mapped, we can visualize the input streams through graph measurement or create a project. I have used illustration as for showing the project that I have created, and then file, this would be the path where the project would be saved. We have used input mapping structure as P and output mapping structure as B, and then we can select the language in which we have to develop or we have to send the data to. Suppose we have to send the data to MATLAB, then we will select the MATLAB or any other language you can select. This is the IEEE 14 bus test system that we have used for illustration purpose. We have used the GTNet PMU, which has been placed at card 1 and GTIO fiber port 12. For our ATC estimation problem, we have used the IEEE 30 bus test system that we have modeled in RSCAD. This here we have shown two areas, area 1 and area 2, and this is the area 3 of the model. We have used GTNet-SKT to communicate with the MATLAB command and control center. The GTNet-SKT is placed on card 1, fiber port 9, with local port 5843. These were the results obtained from the ATC estimation. We have sent two different scenarios from MATLAB to the RSCAD in real time, one at t equal to 40 seconds and one at t equal to 80 seconds. And the ATC corresponding to these two scenarios have been obtained and plotted in figure B. The performance of the ANN estimator has been analyzed and reported in the article. Thank you.
Thank you very much to our presenters today, Dmitrii and Devesh. And thank you all for your attention and for being with us for USS week number 8. Dmitrii is not with us for the Q&A, but we will send your questions to him via email and he will respond that way as well. So no worries there. Devesh is with us, so we will go to a couple of questions to discuss with you, Devesh. The first question is, have you done any work in comparing the accuracy of this neural network-based method compared to conventional STATA, nonlinear-based state estimation methods?
Actually, we have compared with respect to the ATC estimation. Conventional ATC estimation outputs have been obtained and compared with the ATC estimator that had been produced using the reported in article of ITGTD. And when I talk about linear estimators, the focus of work was not on increasing the estimation efficiency. We have used conventional linear estimator that was already proposed in literature. So we focus more on estimating the ATC value.
Excellent, thank you. Also, is there any provisions in the system for bad data detection or identification? Is that work that has been built into this so far?
We are working on that, developing bad data detection or some event detection kind of thing. We are developing some sort of mechanism using information theory where the data streams would be quantized and analyzed and a span over which the data would be archived for post-processing or analysis that is being under development. So we are using transitional probability matrix and transitional window matrix for doing that. So that is the work which we are currently doing in that field.
Great, thank you. We'll have to stay tuned for updates to that. Also, have you done any modeling of active distribution networks in detail within RSCAD in terms of how they affect the available transfer capability and the estimation? Or is this mostly just focused on a higher level model?
Actually, I have developed the modeling of active distribution networks in OpenDSS software that we will be integrating into RSCAD through different time scale. There is substep and superstep. Two different models are there. So we are including our whatever the most our focus is there according to time step. We are having one system in substep, that is main step, and one system in super step, and we are having an interactive simulation there. So that is also we are working on that. And about modeling the active distribution network in RSCAD, that exclusively we have not done, but we will be looking into that in our lab.
Excellent. That's great to hear. Okay, I think that wraps up our questions for today. I want to thank you very much, Devesh, for joining us. I know that it is probably late for you there, so I thank you very much. And thank you to our audience for joining us as well. Anyone on demand, please feel free to continue to send in your questions. And I hope everyone has a great day.